In this session, we'll discuss about a few of the applications of Gauss law. In the last session, we have seen that suppose we have a closed surface and let's say the charge enclosed within this closed surface is Q enclosed. Then by Gauss law, the electric flux emerging from the closed surface is equal to the net charge in the volume enclosed by the closed surface. So Gauss law is applicable for any arbitrary surfaces, but we can use Gauss law advantageously to determine the electric field when there is a symmetry in the field distribution. So please remember that Gauss law is applicable for any arbitrary surfaces, but it can be used to determine the electric field easily when there is a symmetry in the field distribution. Now, for a given charge distribution, to determine the electric field, we need to construct a closed surface. So to apply the Gauss law advantageously for determining the electric field, we can construct what is known as a Gaussian surface. So this Gaussian surface has two properties, that is, at all points on the closed surface, the electric flux density should be either tangential or normal to the case. We'll try to find out the field intensity due to infinite line charge, which is along the z-axis, by applying Gauss law. But for applying Gauss law, we have to construct a Gaussian surface. Since in this case the electric field lines and also the electric flux lines are having cylindrical symmetry, it is advantageous to construct a cylinder as the Gaussian surface. Let us consider a closed surface which is a cylinder of radius rho and height h. So this surface of radius rho and height h has three surfaces. So this is the top surface S1, the sides, that is S2, and the bottom surface S3. So at any point on the top surface S1, we can see that electric flux density D is tangential to the surface. So here this is the direction of the differential surface and this is the direction of the electric flux density. And at this vertical surface, the electric flux density is normal to the surface. So this is the direction of D and this is the direction of ds for surface S2. And for the bottom surface, again the electric flux density is tangential to all points of the surface S3. So we can observe that here for S1 and S2, the electric flux density at all points of S1 and S2 is tangential, and for S2 at all points of the surface S2, D is normal to the surface. And also at all points on S2, D is having same value. So let us try to find out the electric flux emerging from the closed surface. So the electric flux emerging from the closed surface is given by this expression, and so the electric flux emerging from top surface is given by this term. The electric flux emerging from the sides is given by this term, and the electric flux emerging from the bottom surface S3 is given by this term. So here we can see that for S1 and S2, the dot product of D and ds is 0, because the angle between ds and d is 90 degree here. So therefore, for S1, the integral is 0, and similarly for S3 also it is 0. So therefore, the flux emerging is given by only the second term. But here, because D and ds are parallel, the angle between them is 0. So the dot product is now d into ds, and now we are using the second condition for the Gaussian surface here, that is at all points of the closed surface where d is normal, d is having constant value. Since d is having the same value at all points of S2, we can rewrite this as d into integral of ds over S2, and the surface integral over S2 is nothing but the area, surface area of S2, which is 2 pi rho into h. So this gives the flux, electric flux emerging from the closed surface. The charge enclosed within this closed surface, we have to consider only the charge which is present within this closed surface. Since here the linear charge density is lambda L coulomb per meter along the entire z axis, and the height of the cylinder is h, we have to consider only the amount of charge which is present within the surface, that is this portion h. So this charge is given by lambda L into h. So from Gauss law, we can see that 1 and 2 are equal, that is electric flux emerging from the closed surface is equal to the net charge enclosed. So therefore, we get d into 2 pi rho h is equal to lambda L into h, or d is equal to lambda L by 2 pi rho. Since E is equal to d by epsilon naught, the electric field intensity is given by 2 pi epsilon rho. Hence we have derived the expression for the electric field intensity due to infinite line charge, where the charge density is uniformly distributed,